But a standard free fall problem doesn't say to use acceleration of gravity in the problem. They merely assume you know that the object's in free fall. Anything falling or thrown into the air is experiencing free fall. Let me give you an example. For a simple argument's purpose, let's say that you are standing on the ground and you throw a ball upwards into the air. And you throw the ball at 25 meters per second, 50 miles an hour. How high does the ball go before it stops and turns around and comes back? This is a very standard free fall question. Again, you throw a ball upwards into the air. How high does the ball go before it stops, turns around, and comes back? Now, free fall problems generally are predicated or looking for two important details. The first detail, do you understand when to employ free fall and when not to? This ball is in free fall the moment it leaves my hand. Even though it's going upwards, we say it's in free fall because the moment it leaves my hand, acceleration of gravity is the only acceleration it's experiencing. Second, free fall problems are the best place to get screwed up with direction. And that's purposeful, meaning free fall problems are often set up to try and trick you about direction. So in any problem that you suspect is a free fall problem, I would like you to draw a picture and an arrow. And on that arrow, you should decide from the beginning of the problem what direction is going to be positive for your problem. So, what direction would you like me to make positive? Upwards or downwards? So if we decide to make upwards positive, then we can begin the process of identifying the variables acting in the system. And for all intents and purposes, it might appear as though I've only given you one piece of information. But I've given you three. First, I asked for you to tell me how high the ball goes. So its maximum height is achieved when the ball comes to rest. That's an interpretation problem, and you have to know when to interpret that as a result. The second thing is you have to realize that this problem is also based on the idea that gravity is what's bringing this ball to rest. So the acceleration is going to be the acceleration of gravity, 10 meters per second squared. But we chose upwards to be positive, so I suspect you should make downwards negative. From this point forwards, put a positive and a negative next to your vector values. If for no other reason, if you start doing that now, you will be far better at dealing with vectors as the year goes on. Of course, now you've got your three pieces of information. Thunder? All right. There's not a pep rally today, right? That's tomorrow. Freshman. So that's the only question here. I mean, you see that, right? This is all you're going to be doing. Once you know that, this problem is pretty easy. So I don't suspect you'll have a difficult time with it. 0 minus 25 squared equals 2 times negative 10 times delta x. Right? Is that what you did? That's a choice I'm making. I noticed that I wasn't given the time. Because I wasn't given the time, I identified a relationship that had no time in it. Checking my values here, negative 625 equals negative 20 delta x. I'm noticing that my answer is intentionally positive. Is that 31.5? No. Maybe. No. 2.5. And I'll point out that my answer comes out positive. That's good. The ball went up. I was hoping it would. So, a standard free fall problem. Yeah, they can get harder, but we started there. Want another one? I like this one better. It's harder. Doesn't feel harder. You stand and realize you have no friend, so you decide to play catch with yourself. You throw the ball into the air at 15 meters per second. When does it come back to you? Meaning, when will you have to catch the ball if you throw it upwards at 15 meters per second? Let's see if you can figure this one out without my help. And do this problem in one step. Again, you throw the ball upwards into the air. When does it come back to your hand? Done yet? Having trouble? Do you know what your 5 variables are? I see people with calculators, but of course these numbers are not particularly hard. I'm not saying you shouldn't use a calculator. Usually a calculator means you've gotten something. There should be 3 things here, but more importantly, I hope you did what I asked. Is up positive or negative? All right, so we're doing positive again. Great. Some of these are easy. 15 meters per second. Acceleration, negative 10 meters per second squared. The negative and positive here are because you said upwards was positive. I would get the exact same answers if you said downwards was positive. But I need another piece of information. What's my other piece of information? Final velocity is 0 will tell me when the ball is here at its maximum height. But that won't tell me when it's back in my hand. Now you might be able to use that time to figure out when it's back in your hand. Is that what you did? You assumed that it would take the same amount of time to come back? No, I would have assumed that. But you could do it that way. How many of you did it that way? Because that's a pretty typical way of doing it. Yeah, that will work. Should take the same amount of time to come back, so when to get up there, there's a little symmetry there. So that's one way to do it, and would have been fine. There's another way. Yes, sir?
Displacement 0.
Sure. Landed back where it came from. Displacement 0. So when I asked you guys to do it in a single step, that's really what I was intending. To recognize that that's true. Throw out final velocity. Choose a relationship that has everything in it except for final velocity. And that'll do it. You get 2 answers, though. Not a surprise that you get 2 answers. I hope you're prepared for that. First answer is 0. What's the other answer? 3 seconds, that's right. So the ball is in your hand at 0, and the ball is back in your hand 3 seconds later. How fast is the ball traveling when you catch it? I just want to see if there's somebody who's going to say this. Because invariably somebody will say 0 because you caught it. But that's really not the answer to the question that's being asked. So there is a problem with the way people conceptualize the second half of this question, which is how fast is it going when it's being caught? Let's say you are successful at catching it. Would you agree that you will probably stop the ball? Does that make sense? The issue, though, is that the ball is moving when it contacts your hand. So a question like, how fast is it going when it reaches your hand? Or how fast is it going when it hits the ground? They don't want what happened when the ground touched the object. They want how fast it's going when it met the ground or when it met your hand. That's before your hand stopped the ball. So in the case of this problem, we would find that it's traveling minus 15 meters per second. That's how fast it will be going when it comes back to the ground or comes back to your hand. And if you don't believe me, well, let's look for this one, not include time, and look at what our relationship is. That would be v squared minus v naught squared equals 2a delta x. But delta x is 0. So oops. What am I doing here? There, v squared equals v naught squared. You have to be careful. Plus or minus a square root of v naught squared, which means plus or minus v naught. Choose correctly. The answer is not positive 15. The ball is traveling in the opposite direction. It's downwards when it reaches your hand. What do you think? Free fall hard? Free fall problems have the potential to be tough. They have the potential to be tough. Almost always it's a conceptualization problem, or you're not being careful about direction. So the vast majority of free fall problems deal with trying to manipulate your sense of direction on them. So don't be manipulated. In the very beginning of the problem, choose carefully what you will call positive. If I could offer you one thing to put in your notes that will save you a lot of heartache in the future, put it in a big box right now and just tell this to yourself. Do not assume the acceleration of gravity is negative. All you AP1 kids, you know why I'm saying it, right? G shows up a lot in physics. Don't assume the acceleration of gravity is negative. The acceleration of gravity is downwards. All right, last. It has been regularly accepted to use a lowercase g to represent the acceleration of gravity as a symbol in problems where we're not using numbers. Lowercase g is reserved in this case. It still means the acceleration of gravity, but be careful as well. It does not mean gravity. Lowercase g means the acceleration due to gravity. I'll say that again. It does not mean gravity. It means the acceleration due to gravity, which is why I'm saying that so much. It's so wordy. But we will eventually study gravity. And when we study gravity, there is a capital G that becomes an important constant as well. This is not gravity. Gravity is a force. This is the acceleration due to gravity. So if you're writing your answer out and you use this word incorrectly, graders will probably take off a point. So G represents the acceleration due to gravity. That's really it for today. You have enough information to do all of your homework now. Do some free fall problems. There are some easy ones in the beginning and some trickier ones towards the end. None of them are terribly hard. Some of them are mathematically complicated.